Now, I would like to introduce today's speaker. Today's talk is going to be given by Tim O'Shea. Tim is the co-founder and CTO of DeepSig, which is a venture-backed startup that is building machine learning-driven wireless capabilities and optimizing 5G RAN and Open RAN deployments. Tim serves as a research assistant professor at Virginia Tech in Arlington. He previously worked as a USG lab on software cognitive radio applied research technologies and rapid prototyping. He's a co-chair of the IEEE Imaging Technology area on machine learning for communications and an editor of the Transactional Wireless Communications and IEEE Transaction Cognitive Communications and Networking. He's also a co-chair of IEEE GlobCom and IEEE ICC Machine Learning for Communications workshops that are happening in 2020. He's also the chair of the GNU Radio Conference Technical Proceedings and co-author of more than 50 peer-reviewed conference and journal papers with over 3,000 citations and 20 patents. His primary focus is on the intersection of wireless communications and machine learning. Previously, he was a technical consultant for Hawkeye 360, Federated Wireless, O'Shea Research, and Cisco Systems. He has also served as a technical advisory board member for programs at National Science Foundation, NSF, DARPA, EU Horizon 2020, and Department of Defense programs. He completed his PhD from Virginia Tech ECE in 2017 and Bachelor of Science and Master's in ECE at North Carolina State in 2007. In today's talk, Tim will highlight how AI and machine learning techniques are embracing data in order to better shape efficient radio access networks today and in future cellular technologies. The focus will be on how the physical layer can be thought of as a data-driven machine learning problem and what this means for better radio and G-Node B performance in today's systems. He will also discuss how this could be deeply impact future beyond 5G radio waveform protocol design to further increase the efficiency and density. Furthermore, he will give an overview of the work that is being undertaken at DeepSig and Virginia Tech in order to help realize these visions, and also discuss other areas where AI and machine learning techniques hold enormous promise in helping to optimize future wireless systems. Overall, the talk is going to highlight how data-driven competition, such as the ITU AI and Machine Learning 5G Challenge, and data-driven optimization and validation of approaches are important avenue for communication engineers to embrace at many levels of the stack of communication to evolve. So I would like to welcome Tim. Tim, welcome and good morning to today's webinar. Thank you very much for joining today.
All right, so thank you. So yeah, so I'm going to talk a little bit about kind of what we're doing in AI and ML and some of the other work going on in the area, but focused primarily on how we see this impacting the 5G RAN, and then how other pieces of this could go further into kind of the beyond 5G, beyond the current standards space. I think there's a lot of exciting possibilities there. So, all right, so where are things headed in wireless? Overall, kind of starting at the 10,000 foot level, we're already at this point where we have 20 or 30 billion devices, and device count is accelerating. People are predicting 75 billion devices by 25, and over 15 devices per person by 2030. So this device count is just kind of wireless devices in our spectrum is accelerating like crazy. And so carriers are looking beyond just traditional UE subscription. We're going to have this throughout our infrastructure, throughout our vehicles, our factories. And so really one of the driving technology needs here is this fundamental need for better multi-user capacity, better spectrum sharing, better ability to tailor the QoS of the RAN to different applications and user requirements, and to effectively utilize new bands that are very difficult, like millimeter and terahertz wave. So this is a massive demand on wireless, on L1 design, to really have algorithms that can accomplish all of this. And so I think that's really what we're trying to do here. So at a high level, how are these new machine learning or data-driven methods changing the physical layer design approach? So if you look at kind of the canonical communication system design approach, it's to divide our comm system up into these nice modular pieces. We kind of come up with a abstraction for each module, and typically a simplified statistical model of each. So for instance, for synchronization, we typically design something like a map or an MMSE estimator under some sort of assumption, whether it's Gaussian or a Rayleigh channel. But typically it's a nice compact statistical formulation of the problem. Similarly, if you look at like channel coding and error correction, we often assume a nice kind of binary symmetric channel. In our estimation and equalization, we typically assume something like a Rayleigh or TDL model. And then often for our multiple access schemes, we use something like a Poisson arrival process. We don't drive all of this from data today, but we know in the real world, all of these distributions are much richer than these kind of simplified models. And so the goal, in my mind, with using machine learning and communications, is to do a better job of figuring out, based on data, what are these real distributions, what are these real channel models, and then how can we really effectively design our systems to optimize for them. And so, a lot of our thought is driven by this idea of, well, okay, let's think of this in an end-to-end way, where we want to learn multiple of these stages jointly on the real data, and come up with a better, more compact model that better fits the real world than the kind of idealized one. So, how far is our statistical model for the environment from the real model? We have great, strong expressions from physics on, how EM propagation and reflections work. We can do things like ray tracing and very precise EM modeling. But the problem typically is if we think about these kind of really dense urban environments with multiple reflectors and many, many devices, or even kind of indoor environments with many surfaces, devices, coupling, all kinds of effects going on. We don't have all of the parametric complexity to model these in a very rich way. So whether you drive these system modeling from a physical model, kind of a model-based, purely model-based, or more data-driven, you have this massive complexity of parameters to try to define your wireless system. And so I think there's really no way to escape this complexity of data, whether it's model-driven or data-driven. If we want to get to the richness of these environments to try to express all of the actual spectral and spatial propagation phenomena, we really have to turn to these much more data-driven models going forward, and really increase the complexity that we can model and optimize for. So I kind of break this down then into, and these kind of correspond to the two further halves of the talk here. The first actually focused on, how do we improve our access to the radio spectrum? How can we improve this multi-user efficiency? How can we improve our power efficiency and our experience of wireless devices? And then on the sensing side, if we want our systems to be as packed in as possible to the point where we understand what propagation looks like, what interference and adjacent emissions look like, we need this ability to actually sense and measure the usage of the spectrum so that we can efficiently allocate and share it between many devices. So this is starting to look at if we kind of jump beyond standardization and today's standards and think about the basic problem and look at, well, can we just completely treat comm systems as a learning problem? And so autoencoders have been used very heavily previously in computer vision and in image compression and voice compression problems. So they're very, very good learning structures for representing information. And so, some of the earlier work in this area that we looked at, and actually with Jakob Hoytes, who I see is joining, so hello, Jakob. So we looked at, initially, can you learn to encode and to decode information, and then kind of naively learn those encoding and decoding schemes. And some of the initial results really looked at, can you do this for different information rates? Can you do this against existing baseline codes at those block sizes and those information rates? And you could very quickly come up against kind of what is a canonical baseline for very small block codes. And kind of one of the things we've been looking at is really building this out for things like point-to-point systems. So in cases like, one of the efforts we worked on was working with NASA to go over some of their bent pipe satellite links, where you don't have a lot of complicated channel effects, but you do have some interesting high-powered Ka band amplifiers that impart quite a few different, hardware distortion effects. And so, we're showing here on the right, if you baseline a traditional QAM system against kind of an end-to-end learn system, this is a very satisfying result, because it kind of comes up with a constellation that works well under these impairments. It kind of spaces points efficiently for the noise that you're seeing at each level. And in this case, you're getting 3 times the packet pass rate than you would otherwise. So I think, thinking about comm systems that way in kind of this data-driven form begs the question then, what constitutes end-to-end in a communication system? And there's a lot of ways to think about this, and what are the extensions to end-to-end. So, one of the things that's gotten a lot of focus and work is, how do you effectively do online adaptation? So, if we learn a data-driven scheme, well, the channel is changing, temperatures of hardware components are changing. So how do we effectively update between communications nodes, or the UE and the BTS in a cellular case? If you have MIMO systems where there are many transmit or many receive antennas, how can you scale these approaches to MIMO configurations? And then some very interesting work on, if end-to-end is not just the bits or the packets of whitened data that are being sent over the channel, but instead is kind of a structured distribution of some source information like imagery or video or audio, should end-to-end be from the application data to the application data. So some really, really cool work in that area has gone on in this deep joint source channel coding, showing that, you pay a price for wanting to have whitened bits in the middle, and that there's a very significant performance increase sometimes from coming up with these joint encoding schemes. So also very interesting extension to this, looking at multi-user, as well as thinking about not just sending the data over the channel, but if you're trying to send different quantization levels, or trying to encode feedback loops of channel state, and a lot of also extensions now into looking at frame and pilot design, and beyond just modulation, how do you really design a full specification in an optimal way? And a lot of work, I think, also has gone on here very nicely in the optical space, where systems are kind of severely distortion limited, where this sort of closed loop end-to-end optimization has shown some very significant gains in what you can attain over those impaired links. So switching gears a little bit into kind of what's going on more in the industry, Open RAN has grown significantly this year in traction with a number of major operators and a number of vendors, and it's actually becoming a major viable option for cellular systems now. And the big shift here is that traditionally we would have one vendor kind of providing the RAN as a kind of a black box package, whereas we're moving through this first level disaggregation into Open RAN, where you actually now have kind of a whole ecosystem of competitors building radio units and then building these virtualized distributed and central units to do portions of this processing. And I think this is kind of important from a machine learning for communication standpoint, because it relies on data, right? So we need data and we need access to data to do these sorts of optimizations, and we need access to these reference implementations to be able to vet and prove out and deploy these solutions. And so the fact that this is turning into kind of an open vendor ecosystem and an open software ecosystem is really exciting for ML comms, because we can now look at data across all of these aspects of commercial systems, and we can go in and look at numerous algorithms and areas for performance improvement across this entire stack. Right, so Open RAN is really making a lot of these components and the data from these systems and these algorithms within virtualized RAN much more accessible. And so I think that this is really going to help open the entire ecosystem for much more algorithm innovation and experiment and test in real systems than we've ever had. And yeah, so I think that, on the other side, Open RAN suffers right now because it doesn't have the same level of R&D and performance optimization that many of the kind of tier one vendors do. But this is, I think, like, for me, this is extremely exciting, because this is the opportunity in that there's many opportunities where you need that performance. You really need to compete with state of the art and beyond the state of the art. And this is a way that you can start doing it in real systems. Our focus and what I'll kind of talk more about here is primarily within the L1 of 5G, but I think there's tons of really good work going on within the L2 and the L3, looking at scheduling and resource management and coupling specific applications with these sorts of systems. And that kind of R&D is now going on a number of places. So, where do we see this major potential within the G node B? And I think, back to this idea of model deficit, where our channel models didn't match reality, or the complexity was too high. Well, if we can have our G node Bs do a better job of learning the actual distributions and the properties of the local channel, then they can better cope with local interferers. They can better exploit kind of spatial modes in the environment, and they can generally do a better job of leveraging information to optimize for transmission and reception of data. And so, we initially built out kind of a vRAN to do this in kind of a small TDD way, and saw that this did indeed work very well during interference events. So if you use a data-driven approach to recovery of information in the uplink, then you can kind of start learning how to suppress common sorts of interference without ever having to model or specifically build cancellation or those sorts of things for those interference. And the other big takeaway here was that a lot of these methods, the machine learning driven comms methods that we're talking about, can be used directly just in implementation of today's standards. So we know many of the signal processing functions that are standardized within 4G and 5G, and many of them we can implement using these ideas and approaches. But then I think there's this even larger realm of possibilities when we start looking beyond that, if we start allowing certain types of feedback or adaptation over the link. And I think that's kind of the differentiator that I think exists into this beyond 5G and 6G space, where we think about really what is possible, what could be the candidates of the future. And so, I think this is one of the big changes in comms R&D that's either here or coming, is that this measurement data in the loop is really critical to showing significant advances at this point. So simulation on kind of smaller models, compact models, is often a necessary step, but is rarely sufficient now to be able to look at coping with this very dense environments that we have to cope with today. So when looking at kind of learning in the uplink, in 5G NR for standard MIMO, this typically includes doing estimation on the DMRS reference signals within the PUSCH uplink. And so some of the work that we've started to look at here is like, what if you have many users in a sector and you want to be learning from all of them, and you'd like to come up with a consolidated uplink reception model that works and it generalizes nicely to multiple UEs within a sector. And so, this is some kind of work in a smaller UE count scenario where we're looking at doing that. And in this case, we had performance that was actually slightly better than initial simulations, where we're seeing 5 and 6 dB reduction in both EVM and Burr versus the kind of canonical MMSC and Wiener filtering approach. And the really exciting thing with Open RAN is that you can leverage radio units and stacks to put this into commercial equipment, into commercial ready deployments, and really test this with standard UEs. And so really start vetting this at the, does it work in the real world level of simulation very much more quickly within this development cycle than would be traditional. So then, it's also critical to say, do these things work under the actual 3GPP acceptance tests and kind of performance tests? And so, looking at some of the very rigorous approaches for simulation using the TDL models that are specified, you can look at specific FRC modes. And here we're kind of just showing 2 of those modes. This is a 1x4 diversity uplink reception and a 1x8 diversity uplink reception. And at moderate SNR, 6 dB, and then at very low SNR of minus 9 dB. These are 2 kind of nice cases where this a purely data-driven approach converges very, very quickly, comes up with a very nice solution, and in this case you're able to get 3 dB of EVM or 2 dB of EVM in these 2 different scenarios, versus kind of the canonical approach. And what's even more exciting is this can be done with very small models, like less than 10,000 parameters, that can run much faster than conventional algorithms. And so not only can we give these sorts of systems more capacity to use for throughput and multi-user efficiency, but also we can save on compute costs and help make these systems cheaper and easier to deploy. And then these approaches, really have a benefit as well when you start looking at, when we scale from these standard MIMO numbers of 4 and 8 up to much larger, massive MIMO configurations like the 32 and 64 TRX systems. These sorts of models just scale much more linearly in their complexity. And so this is really, I think, an exciting area for, how can we better exploit spatial degrees of freedom in massive MIMO, and then also kind of the ultra massive MIMO that people have been discussing for further out, where we just have even more elements, and also often maybe even less well-defined elements that might not just be linear arrays like we use today. So kind of switching modes to the sensing side, that was more focused on how do we use the spectrum. We're looking at, what is this need for sensing the spectrum? And so, spectrum sharing has kind of become real in a very real way in the US, as well as I think much of the EU and the UK. And so if you look at the CBRS and the 6 gigahertz bands that have been approved in the US here, these are going live, right? So we're going to actually start operating with these shared environments. Today these are very heavily database driven. Licensees need to register in the database to get authorization to use the spectrum. And then there's kind of opportunistic access on top of that. However, these really rely heavily on the fact that the database systems, like the SAS, as they call it, can model, how much do these systems interfere with each other, and what sort of distance and spacing and reuse is feasible and safe. And this can be really hard to model, especially in dense environments and where it's not just free space path loss, it's wildly more complex than that. And so, we're going to see limits on how far we can get with purely database-driven methods. And so, likewise, when we look at 6 gigahertz band, it may be less coordinated by databases, but also it's going to have many different private users of private LTE, NR, and Wi-Fi systems that really need to be able to interoperate nicely and be aware of their adjacent users, be aware of interferers and other protocols in the band, so that they can really optimize their interoperation. And so I see that this kind of, as we get more and more dense devices and deployment and spatial reuse, all of this becomes much more critical for the efficiency of our wireless systems, as well as the security of these systems as we start to have emissions in these bands that we just need to know what's going on. So if we look at a high level at these kind of trade-offs for if we want to have this spectrum awareness, what are all the approaches we can look at? So we've long had very general models that work for many sorts of data, looking at things like energy detection or radiometers, and then we've also long had these very high sensitivity approaches like match filtering that, at least in a Gaussian channel, give you great sensitivity at kind of a higher complexity cost. And so there's kind of this big trade space over different types of feature-based detection, and using different amounts of waveform knowledge to come up with different levels of generality in your sensing capabilities. But I think this kind of emergence now of these, almost purely data-driven sensing techniques is really exciting, because we can get kind of both. We can get very high accuracy and sensitivity, and we can get very low model complexity, and we can get very good generality across many different types of emitters and protocols in the spectrum. And so, if you look at computer vision in machine learning, you also have this whole architecture evolution, where if you think of these models as representing just this ML sensing models space, you know, as we get better and better and better at coming up with efficient neural network architectures, this operation complexity and your accuracy metrics are both improving and kind of moving in this upwards and left direction, so that this, you know, this class of models is just continuing to move upwards and left, kind of to advantage it over these kind of more static methods that are typically more fixed in their algorithmic expression. So some of the earlier work looking again at, in this case, you know, single emitter classification. So if you have this wide band of spectrum, and you just look at, you know, one carrier in this entire spectrum, and you want to say, you know, what type of modulation or carrier is it? You know, it's really exciting to see that if you apply some of these methods, you know, simple CNNs work very well on this. You can wind up with very computationally efficient sensing, which gives you significant sensitivity improvements. So, you know, in this example, this was on the order of 6 or so dB of sensitivity improvement. But, you know, domain knowledge, so ML is a very powerful tool, but the domain knowledge is also really critically important here. So, you know, the data that you're training against, that you're building these systems on, has to really match the real world data distributions that you expect to see. And a lot of this comes into the form of, you know, what are the emitter types, what does the propagation look like, and this idea of augmentation. So really being able to simulate all of the possible things that you will see and that could happen in the spectrum as you train and test and vet these systems. So that's kind of the simple half of the problem. The other big piece is, well, you know, we don't actually know if there's many different users and technologies. You know, what are the channelization plans? What are the different users present? And so this problem of wideband detection is also kind of a critical one. And so, you know, if I just turn on an NR unlicensed G-Node B, and I want it to, you know, figure out where to operate, you know, it needs to you know, rapidly look at what are all the emitters in the area, or is there EMI, are there different types of emissions that I should work around? And so, you know, this is some work that Nathan West has done recently, you know, trying to look at in a nice, well-controlled environment, you know, what are the sensitivity advantages to doing this using a pattern recognition and CNN-based approach, you know, rather than kind of a more traditional radiometer and energy-based method that's used today. So, you know, all of our systems are designed to just look at RSSIs and kind of make decisions based on that. And this is, you know, insufficient, I think, for where we're going and the device density and coordination that we're going to need to do in the future. And this is also still under a Gaussian model, and so this is kind of a worst case in a way, in that it's still not leveraging the data of many real-world propagation scenarios. So putting this all together, you know, we think that this kind of spectrum awareness is really key for these sorts of systems to be able to operate, you know, in a shared spectrum environment, and for us to be able to pack in spectral reuse in these shared spectrum environments as efficiently as possible. And so it's really exciting that you can really kind of put these sorts of models together, and you can come up with extremely accurate, you know, 1 millisecond level characterization of all the different emitters in the environment in a way that really just wasn't practical before. And so I see this kind of as a key enabler as we get to denser and denser systems that all have to kind of play nicely with each other and discover, you know, each other. This also is really exciting in that, you know, we're turning the spectrum into something that we can now start to do, you know, very nice structured analytics on. And so, you know, today, if we look at, network analytics and trend analysis. We have this nice packet data and nice counts and events that are very discrete and easy to work with. And so, this sort of ML-driven front end also allows us to, turn the spectrum into this similar structured data. And so this allows us to have records over days or months or weeks or years of, literally what are all the different activities going on in the spectrum, and when do changes occur, when do new devices come online, when do anomalies happen, as well as things like doing much better forecasting of, what is the overall spectral utilization of all of the different emitters in a band, so that if we need to surge for events or for capacity or different requirements, we now have these very good models that we can build over all the emitters in an environment to help enable this. And so this is, just longer term trend analysis on single uplink bands. We can very quickly see the kind of behavior in a work week versus a non-work week. And here there's just a lot of nice time series prediction modeling and anomaly detection modeling that can help enable this. So where is this all going? I think, there's so many interesting places that this can fit into these beyond 5G or 6G kind of models of the RAN. I think, we've talked about the requirements. I mean, the requirements are always an order of magnitude more of everything. In this case, we'd like that in terms of driving down processing power, making them more efficient, driving up content rates, data rates, improving this spectral reuse and spatial spectral efficiency across many users and many devices, and then scaling to many more billions of devices throughout all of these systems. And so these are kind of the tall requirements that everyone would love to achieve. And so I think the channel encoding that we've talked about is kind of the beginning of the problem. I think that's a really powerful approach to looking at how do you do better multi-user and multi-antenna and MAC reuse or optimization under all the real world constraints. But there's a lot of other issues around, how do you do CSI encoding and feedback to reduce overhead? How do you really efficiently do feedback and learning for not one, but all of the UEs in a network? How do you learn the best sorts of frame layouts and reference tones to use? And then how do you leverage temporal information, and over time where you can kind of exploit more of the dynamics you've seen in the past to help with all of these problems, and then further leveraging location within all of these algorithms. I think one of the things that folks have discussed for 6G is really just scaling the spatial reuse component. And so this idea of going, rather than, one 64 element array to, the side of a building with hundreds or thousands of elements, we get to this point where we don't have these nice uniform linear arrays. We have very dispersed non-perfect arrays, and so how do you make use of that efficiently, especially if these are desired to be cheap devices that aren't perfectly linear, and they might be constrained in their dynamic range and their quantization. So how do we really make use of these effectively? And I think this is one of the most exciting areas for machine learning is being able to optimize over all of these constraints in a way that we really have a hard time doing with today's kind of approaches. And I think, right, then we've talked about kind of the spectrum awareness. I think today there's today, operators really just look primarily at network level KPIs. And that's a great place if you're just looking for kind of catastrophic failures or service disruptions. But if you want to have this kind of detailed information of what's going on over the RAN, you really need this sensing, and it doesn't all have to be at the G node B. So, if we're adding sensing in all of the radio units, that gives us a lot of information to optimize on. If we have that sort of sensing in the handsets, we can have even richer models for what is the actual spatial spectral utilization look like at the current time. And then this whole problem of taking all of that information and efficiently feeding it back upstream into the network to optimize allocation and resource usage. And so really it all comes down to a lot of different methods for how do we learn to best encode and decode our channel data, our source data for certain specific kind of special applications, how to exploit all of these spatial degrees of freedom, how to really enable our resource utilization through awareness of what is actually, fully being utilized and where is it propagating and where is it causing interference. And then the ability to really compensate for lower cost, non-imperfect hardware and interference. And I think that, all of these areas are kind of critical areas that the AI and ML can play a major role in driving in the next generation. And so I think it's a great time for anyone looking for kind of research areas here, because there's this huge wide open field of things that are, I think, going to be critically important. So I'll kind of end on that note. We're, I think, having a lot of fun trying to take these systems and ideas and really build them out. And I think Open RAN and machine learning for comms happening at the same time are really exciting because they feed off of each other. They allow you to go and try these with real data in the real world, and then have mature, proven algorithms to go and have major impact in these sorts of systems in the real world as well. So, and I think a lot of the work that both the ITU 5G ML group has been doing with these sorts of challenge problems, as well as the IEEE ETI MLC sorts of challenges and data sets and problems are really awesome enablers for trying out and embedding these sorts of approaches and algorithms. So yeah, love to hear if there's any questions. Feel free to reach out.
Thanks a lot, Tim, for the nice presentation. Now we are going to dive into the Q&A session. So I would like to invite my colleague Vishnu. Good evening, Vishnu.
Yeah, thanks, Thomas. Quite an exciting talk, I should say. In fact, I did not realize that time was passing. So thank you so much, Tim. I think it is quite an interesting talk. I want to ask one question which is in my mind as well, but I do see it in the Costas is asking that as well. So at the rare events, there are unexpected events especially in the network. Sometimes error cases, sometimes alarms, sometimes other types of events. How do you see these mechanisms that you described would work in such scenarios? Especially, I would give it one more spin in terms of training the models, as well as in terms of applying the inference and the accuracy of what you see in terms of results. So what are your comments on that, please?
Yeah, so I think there's a couple ways to look at that. So these rare events, I think from the sensing side of things, right now, these can be very difficult for operators to diagnose. If you're looking only at KPIs and network statistics, then if something's happening intermittently, or there's no easy way to do this in an automated way, it's costly to send an engineer out to the field with spectrum analyzers to really track down and figure out what's going on. And so I think ML in the RAN for sensing is really exciting for identifying and tracking down and automating the resolution of these sorts of rare events. I think if you look more on the baseband, kind of the L1 side of things, rare events I think of as, the UE in your sector that has, a wildly different channel statistics than the others, right? And I think that there's still a really interesting trade space here around, like, how stable are the channel statistics in a sector? How correlated are the channel statistics for the different users in a sector? That might be, there might be a high-speed road next to a walkway, right? And you're going to have wildly different ones. And so I think there's a really interesting area there around, what is the learning capacity for these distributions of channel statistics, as well as the kind of instantaneous channel statistics. So certainly, as channel statistics become much more dynamic and change much more quickly, this becomes the hardest area for ML comms, because the worst case, we wind up back at a pure statistical model that has almost no structure to it that we can exploit. So I think we'll need to build out these systems to be able to handle the different rates of change and the different stabilities of these sorts of users and events, for sure. And I think and I think a big piece of that can be sharing experience and statistics over many cells and over long periods of time, to try to kind of learn and compensate for these rare events.
I think, yeah, thank you so much. That makes sense. In fact, that brings us to one of the questions here. You did describe about Open RAN and ORAN and its architecture, and maybe how it is enabling this kind of interfaces for you to exploit the data which from the network in such architectures. Actually, the question is what is needed in and whether you have such interfaces available for extracting data, training ML models, deploying such ML models in the ORAN architecture and the networks based on ORAN architectures. Whether you have, what should I say, organic native standard tools and APIs and interfaces provided by ORAN, or in your experience, did you have to do some customized interface to kind of build these models in, if I can call it that? Could you share your experience with respect to that?
Yeah, so I think we started out building a lot of our own tooling, so kind of our own UE and GNodeB software and simulation for these sorts of environments. But I think we've kind of evolved towards, there are now mature software stacks out there for doing the L1, the L2, the L3. And so these are becoming more and more available, and many of them are quite open software-wise. So many of them have existing open data interfaces on the inputs and outputs, and then many of these packages also have internal interfaces for debugging and accessing kind of intermediate data and values. So we've spent a fair amount of time trying to work with the some of the ORAN stacks that are being adopted and being widely used, and then definitely building up much of our own tooling to help make sure we can get all of the right intermediate values. We can compare to baseline performance. We can really evaluate these both in simulation and over the air and do data recording within these sorts of systems. So I think this is just becoming more and more accessible. And some of them, like the EURCOM and the SRS tools, are really out there, like completely open source, to help make this sort of data and simulation and access to all of these intermediate values and algorithms possible.
Understood. Yeah, thank you. Actually, Alex is asking another question, which is right up in my mind as well. So, you know, ITU being a standards organization, we are very interested in standards, so to speak. So, I mean, you touched upon some of the aspects of it. In fact, Jakob mentioned it in his, in really interesting aspects in his talk as well. But let me put it this way. In case of how this kind of standardized approaches has helped you in your experience, and also how do you think the impact to standards is going to be? I mean, the part B of my question is a little bit more interesting to us, even though the first part is interesting as well, because we would like to understand. You did mention about in the case of structured data analytics, I think you had a slide where you were talking about time series and so on, and where you did say that the availability of standardized formats, if I understood it right. So that kind of monitoring tools, you were talking about monitoring tools. That's that kind of seemed to have helped you quite a bit. So that is good to know. But at the same time, where do you think this is going to impact us? You did talk about the changes in terms of G-Node B receiver learning. So in one of the slides, you did talk about G-Node B receiver learning. There you did talk about certain types of feedback which can be built in maybe later, which can help this kind of mechanisms. So part A of the question is that how standards help you to some extent maybe, and part B is this kind of where do you see the impact to the standards? Are they revolutionary changes? Are they evolutionary changes? Or what do you think about that?
Let's see. So I think, you know, certain ones, like I think moving to this vRAN architecture where you have this open ORU front haul specification, you know, has been an enormous enabler for us, because you know the L1 on the DU is kind of pure software in many cases, or software plus FPGA, and so having that abstraction, I think, really has drastically opened up the diversity of who's building components and solutions in these spaces, and how easy it is to start plugging in and modifying, you know, software on a generic vRAN environment versus, you know, on a heavily integrated, you know, unit. I think, you know, there's other places. I think right now within Open RAN, the interfaces and split between the L1 and the higher layers of the stack are very well defined and helpful. You know, I think the biggest function it's had is really just opening up the ecosystem. So, you know, the standards are valuable, but you also, it's very valuable once you have, you know, reference implementations and actually vendors that are, you know, doing this test and interoperation and making these things work. And so that, I think, enabling that to happen has been a big piece of it. On the data side, I know that there are some standards. I know both GNU Radio and DARPA and some other folks have promoted certain standards, which I think help accelerate research, and they help, you know, just reduce time spent formatting and wrangling data. So I think, you know, as we come up with more standard ways to store and interchange data so that people can do more R&D and algorithm test and improvement in these areas, it's very valuable to be able to have those sorts of standards. And they don't always need to be, very complicated, but it's nice to have something that, isn't a totally new format where, for every different group that's working in this area. But I think it's hard to know right now, where are all the places we need standards. There's a lot of different places within the stack and different scenarios that people are thinking about. And, it's, I think it's a challenge to identify probably where standards would impact those mostly a priori. I think for ML, we've often wound up with, some kind of a de facto standard by kind of early experimenters. And then, but as this all goes into really larger production, as we're having different vendor base stations interchanging the sorts of data and sensing data and model data throughout a network, I think those are going to become more and more important, and we'll get a better idea of really how to start nailing those down.
Thank you so much. I think you're saying we got more work to do. So thank you. That makes sense. It's quite exciting. You did talk about data quality. I think it was in the context of single signal classifier performance. That slide you were talking about augmentation. You were talking about real world environment, and you did talk about things which are practical now, which were not practical before, which kind of caught my attention. So I think the question around that is Ronan is asking, how do you train for anomalies detection in spectrum sensing? I think you mentioned this previously, and also how to detect new RF signals. I think it has to do with the generation of data, maybe the capability of the simulators that we use. In the challenge, in the ITU challenge, we had this problem statement for channel estimation, and we did use a simulator, which I think you mentioned as well, a ray tracing based simulator. We did use that kind of a simulator for generating data. But coming back to the question about detecting anomalies, training models to do that, and also to detect new RF signals, I think this has to do with, again, the type of data that we use. Could you comment on this, please?
Yeah, so I think it's interesting to look at, computer vision as an analog, because there's many different computer vision systems out there, and many of them are using similar techniques, but every one kind of does a lot of their own pipeline and training optimization. So I think we're seeing more and more literature that goes into more detail about how do people do augmentation in radio systems, and we're starting to see more tools out there. And so I think that whole area is kind of developing. And I think from the anomaly detection point of view, it's hard to look at anomaly detection often from an augmentation point of view, because you're presupposing that you can synthesize these anomalies, and so they would kind of be a known anomaly. So I think what we've looked at is you take all of the propagation and RF tools that you can, and you build kind of supervised models and tools using those. And then, there's a number of unsupervised methods that you can then use to look for anomalies. And then there can be a very nice feedback loop by which you identify and curate and pull those back into the kind of supervised pipeline to continue improving your models and your augmentation and your known unknowns, essentially.
Mm-hmm. Thank you. Thank you so much. I think we are running out of time. Thank you so much for staying back and answering these questions patiently. I have to say that this is a very interesting presentation. I will go back. I really liked your last slide. So I will go back and look at it. It kind of gave us the direction to go in the future as well, the open set of problems. I think that is quite interesting. Definitely one of the most interesting talks that we had. Thank you. Over to you, Thomas.
Thank you very much, Vishnu, for moderating the Q&A session. A very big appreciation to our speaker today, Tim, for the wonderful talk. We understand that you are busy, but you made some time to be with us today and to share with us quite an interesting topic. I would also like to thank everyone who joined today for attending today's episode in the webinar series presented to you by the AI and Machine 5G Challenge.